We get to the next presentation, which is online. University of New South Wales, we have Bin Dong. He will, I think it's he, must be, but anyway, we'll see. The novel numerical system for predicting chloride ingress into green cementitious materials. And the very quick summary on that project explores a robust numerical framework for modeling the intricate aging corrosion process of long-serving reinforced concrete structures. And then we have to acknowledge the partners, the early project partner, Future Innovative Technology. So if you can ask Bin to do the presentation.
Can you hear me?
Yes, very well.
Yeah. Good afternoon, ladies and gentlemen. Let's guess, water is the most consumed substance in the world. I believe everyone knows it. It is water. If I ask what substance is second most used, possibly not everyone knows. Some people will say steel, wood, or plastic. The answer is none of them. It is concrete. The massive use of concrete brings us beautiful and convenient structures, but it also causes environmental crises. This is due to the production of cement, which is the key composition of concrete. As reported, the material is responsible for 8% of the global carbon dioxide emission. With a worldwide commitment to achieve net zero carbon dioxide emission by 2050, we must find a solution to replace cement in concrete. In recent years, it was discovered some industrial wastes are great candidates. By doing so, not only carbon dioxide emission can be reduced, a recycle option for rubbish is also generated. As can be expected, this new generation green building materials will be widely used in practice in the following decades. When a novel material is in service environment, durability issues have to be considered. Penetration of chloride is one of the most serious problems, especially in the offshore environment with abundant chloride source. Chloride can penetrate concrete and trigger the corrosion of reinforcement. Also, the generation of rust in corrosion process can lead to the cracking of concrete cover. Consequently, the structure is in risk of collapse. Reliable performance-based design and maintenance plan are the key to avoid these problems. To provide a guideline, we develop a physical-chemical prediction system for green cementitious materials. All of the materials share the same modeling core, and time-dependent chloride distribution can be obtained with high fidelity. The numerical system is carefully validated against experimental work. I hope and believe this work can facilitate the application of the new generation materials and contribute to the further exploration on replacing environmental unfriendly cement. Thanks for listening.
Thank you very much. As we know, whatever we do supporting that work with the numerical modeling is quite important, because without all that supporting and validating, we can't validate the lab work. Once it's validated, it's very easy to extend. And so it's a I can see many projects are like that, where to bring that numerical components as well. Today we had some very good presentations on that. So I'll just first see whether there are any online questions.
How long does concrete last in a city compared to concrete and water?
Oh, sorry, can you repeat the question?
How long does concrete last in a city compared to concrete in water?
So it's really like immersed in water compared to the ordinary. They meant city? In situ?
City.
Cities?
Oh, yeah, city.
Oh, in the city, yeah, sure, yeah. So rather than immersed in water, yes, yeah, sure.
Yes, the chloride ingress problem is common for reinforced concrete structures. In some cities, we always spray some salt water on the road. So this is this is a common reason for the chloride ingress, and in the water, there is some chloride in the seawater. So I can compare how many times the concrete in city or in the water, but we can solve all the problems in the city and in the water.
Thank you. Any other questions? Yes.
And another question. So when talking about durability, we tend to think long term. So the question is whether your model would be able to consider all aspects regarding long-term performance, so for example, decay.
In terms of the chloride ingress, I can. In the chloride ingress, the two common mechanisms govern the chloride ingress process. One is the calcium leaching, and the other one is chemical bending. So these two mechanisms all can consider in my modeling framework. Thank you.
Thank you. Any questions from here? Yes. So anyway, continuing from, because numerical modeling is not easy. I think you may have answered this question, but so what sort of platform you're using for your modeling? Your own
actually, I'm using the MATLAB and C++ code. This is a combination of these two languages.
So you have some control over the what
yes.
you develop rather than using other available tools. So I think it's very good. And so with the chlorides, is that are you just you mentioned about the chemical side as well? Now so chemical is not easy to joining. So how do you incorporate the chemical side of the chlorides into your numerical modeling?
Yeah. Actually, I'm using the thermodynamic technique called Gibbs free energy minimization. Is a very popular and new approach in the literature. And I couple this thermodynamic technique with my chloride transportation model. This is the key of my study. Thank you.
That's excellent, because I think that's a very difficult one to tackle. So looks like we are going to get some very good results from you, which really, I know again that it's a project which I'm sure Professor Wego would be your supervisor. Vega, it's Vega. So he's a friend of ours for a long time. TREMS always supporting. So let us acknowledge him, Professor Wei as well, for that excellent work. So we make a contribution, significant contribution. We all can use some of your models being developed. And just one last question. This can be extended to other the carbon dioxides and other parameters, right? That modeling technique you're using, it may not be just confined to chlorides, can be extended, right?
Yes, sure. It can be extended. This is more like a research module in the commercial software, something like that. Yes.
That's very good. I think Professor Wei wants to make a comment as well.
Yeah, thank you very much, Professor Mandis. And the platform actually a student use actually is the codes developed by himself, and actually supervised by Dr. Yu Guoyu. So I'm sorry I couldn't make it to be attending the wonderful event in person. And so today actually I listened lots of wonderful presentations. Congratulations to all, and thank you very much.
Thank you very much. And we all have to acknowledge, I know you can't be here. You have always supported us. Your pioneering work, which is your Australian, is one of the leading leaders in this particular field. And we all have to really acknowledge what you have done as a significant contribution to this area. And also it's a very, how much you have supported TREMS as well, to Professor Jiva and myself and the whole TREMS team. So thank you very much again. So can we show our appreciation to again? So,
yeah, thank you very much. Thank you.
Thank you.